This conference will now be recorded.
Introduce Tahereh Nematiaram. Tahereh is a researcher at the University of Liverpool. She received a double PhD in nanophysics and photonics from the University of Grenoble Alpes and the University of Tabriz in late 2017. Then, as a postdoctoral researcher in material science, she joined Professor Alessandro Troisi's group at the University of Liverpool. She's interested in developing quantum models to explain the fundamental physics dominating molecular materials and junctions, and then making them affordable for the examination of hundreds of thousands of systems by using rigorous approximations. Exploiting such theoretical models, currently her research is focused on discovering materials with targeted optical and electronic properties, determining the realistic physical limit to such properties, like how well can one expect them to optimize them, and deriving strategies for inverse materials design. Today we'll learn about how she's utilized the CSD in her work from her presentation entitled Organic Electronics from Structural Database, New Materials and Design Strategies. Tahereh, over to you.
Thanks a lot for the introduction and for giving me the opportunity to present my research. Good afternoon, everyone. So I'm going to talk about some of our recent work on organic electronics from a structural database. Just before to get started, let me thank my collaborators, in particular my PI, Professor Alessandro Troisi. And with that, let's get started. So basically what I'm going to show you today is that how screening the Cambridge structural database can be used to discover materials with targeted optoelectronic properties, to determine the realistic physical limit to such properties, and to drive strategies for inverse materials design. The focus of my presentation today will be on a subset of molecular semiconductors extracted from the Cambridge structural database, because these materials class have shown great promises for organic electronics technology. So as you know, the organic optoelectronic devices are taking role in our everyday life. One of the most important parameters that affect their efficiency is their charge carrier mobility. So basically, from a technological point of view, it's quite important to have a prediction of the charge mobility in a given material, and to have a broader picture to understand by how much actually we can improve the mobility. So for the first task, we need to compute the material's characteristics and then mobility from such characteristics. But for the second task, actually, we need to compute the mobility for a large number of structures from the same materials class. And then we will have some estimation of the largest plausible mobility in this materials class, and we will see by how much actually we need to improve the mobility. So when considering a large set of structures, in particular molecular semiconductors, this becomes challenging. And in the next 3 slides, I'm going to briefly explain what are the challenges and what we have solved these difficulties. So basically, in molecular semiconductors, molecules are held together by weak van der Waals forces. So there are large thermal fluctuations even in the room temperature. These fluctuations are called dynamic disorder. So the charge transfer integral strongly depends on the relative position of the molecules. Therefore, in the presence of such fluctuations, it gets modulated. So it's quite important to kind of quantify the amount of these fluctuations. And to do so, we need to compute the non-local electron-phonon coupling, which itself is a dot product of the gradient of the transfer integral and the normal phonon modes. And by having this parameter, actually, we can simply compute the dynamic disorder, the sigma. The main problem is that the calculation of dynamic disorder is quite demanding, and as a result, the current theoretical methods could not evaluate this property for more than a handful of structures, meaning that they are not feasible for large-scale calculations. So to overcome this problem, actually, in our recent work, we have developed a novel multi-scale QAnon approach, which basically enabled us to compute this property for thousands of structures. So I skipped the details, but if you're interested, it can be found in the given reference. The second important point about charge transport in molecular semiconductors is the fact that their mobility is like in a kind of intermediate regime. So it cannot be described by the conventional theories developed for the fully localized or delocalized systems. So as a result, over the years, a number of advanced theories have been developed. So they have been really successful in reproducing the experimental measurements. But the point is that the majority of them rely on quantum dynamic propagation. So again, they are not feasible for large-scale calculations. Fortunately, the recently developed transient localization theory provides a unique framework to compute the mobility using a simple analytical formula without needing to any basically quantum dynamic propagation. So that's a really excellent tool to be used for screening. So with this knowledge, actually, we started screening the Cambridge structural database for high mobility structures. We have been using CSD Python API to this aim. So in the first step, actually, we looked for molecular semiconductors and identified 40,000 structures that are semiconductors and computed the charge transfer integrals for all of them. Then in the second layer of screening, by keeping those showing decent band, we ended up with 5,000 structures and have computed the local and non-local electron phonon coupling and also the mobility for all of them. And at the end, we ended up with 40 high mobility structures. The molecular diagram of some of the hits have been shown here. The really interesting point is that some of these high mobility structures initially were not synthesized for transport applications, and in the screening actually we identified that they are pretty good in terms of showing higher mobilities. So basically identifying a list of high mobility structures was only one of the objectives of our research. The second question was that can we identify what parameters are affecting the mobility the most and basically to rank them in terms of their importance. So to answer this question, we computed the correlation between the mobility and the physical properties and actually understood that the molecular area, the dynamic disorder, transfer to dimensionality, local electron phonon coupling, and the largest transfer integral are the most important parameters affecting the mobility. And basically the correlations become stronger for increasing values of mobility. So at this stage, we had a collection of high mobility materials and we had an understanding of what are the parameters actually affecting the mobility. So the ultimate question was to like have an estimation of, so finally, what is the achievable mobility in this materials class? To answer this question, in the first step, we computed the correlation between the parameters. Sorry, here I'm missing the label, so it should be molecular area. And our results showed that the parameters of interest are either uncorrelated or constructively correlated. So this is fantastic. That means if you improve one of the parameters, you would not destroy the other ones. So like with a peace of mind, start improving whatever you like. And then let's see what is the maximum achievable mobility. So actually, as you can see here, by setting these characteristics in their top 15 percentile, we can achieve a mobility of around 7 centimeters squared per volt second. And we observe a 10-fold increase by pushing these important characteristics to their top 1 percentile. So in some way, this 70 centimeters squared per volt second can be considered as the largest possible mobility in this materials class. So I'm pretty sure now you are wondering, okay, so how we can improve these parameters, so to set them in the top 15% or 1% or whatever. So the point is that for the majority of these parameters, the 5 parameters that are listed in the previous slide, there are some general design strategies, more or less design strategies in the literature. The only one which remains without any design strategy or any general design strategy is the dynamic disorder. Because as I said earlier, the calculation of these parameters has been really challenging. And so if the number of studied structures is so limited, basically the structure property analysis does not make a sense. So at this point, actually, we had a unique large set of computed dynamic disorder values, a library composed of 5,000 entries. So this was a really excellent opportunity to go into the detail and figure out what are the materials characteristics of those showing a smaller level of dynamic disorder, and basically how can we design such structures. So we identified a large number of properties related to the molecular topology, the stoichiometry, the frontier orbital energy levels, descriptors of the HOMO, and crystal descriptors. But the point is that we didn't find appreciable correlation between dynamic disorder and the majority of these parameters. And here in this correlation matrix, I'm showing only those showing like meaningful correlation. As such, we observe that there is a acceptable correlation between the gradient between the dynamic disorder and the gradient of the transfer integral, the pairing geometry of the molecules, alkyl chain, transfer integral, and the presence of heavy atoms. Just let me tell you, here I have dynamic disorder and relative dynamic disorder. So by now you are familiar with the dynamic disorder, as I explained earlier. And the relative dynamic disorder is simply is the ratio between this dynamic disorder and the associated transfer integral. And since this relative dynamic is what is ultimately felt by the charge carrier, we have computed the correlation between the parameters and also the relative dynamic disorder. In the next few slides, we will see how actually these parameters affect the dynamic disorder. The first important correlation was between the relative dynamic disorder and the gradient of the transfer integral. So this means basically the dynamic disorder is somehow, like let's say, is mostly an electronic property, mostly, but obviously not entirely an electronic property. So it has two main implications. The first one is that basically we can use approximate phonons for dynamic disorder calculations. And the second implication is that given the relative position of the two molecules, we can predict if the dynamic disorder is going to be large or small. As such, for large-scale screening, maybe it would be more plausible to screen for smaller values of gradient of the transfer integral rather than a smaller dynamic disorder. The second important correlation was between the relative dynamic disorder and the pairing geometry of the molecules. This one is quite interesting. Basically, what we observed is the following. We observed that the molecular pairs arranged in a head-to-tail configuration, but with their conjugated cores not lying on the same plane, as shown in the top row, they show the smaller values of dynamic disorder. So the reason is that in this molecular configuration, the molecular orbitals overlap through the region of orbitals where there aren't many nodes. So this observation is quite counterintuitive because this field has tried for years to increase the number of pi-pi stacking, and now our results is showing that actually minimizing the pi-pi stacking is suitable for other optimals, so is suitable for decreasing the dynamic disorder. The third important correlation was between the dynamic disorder and the presence of side chains or alkyl chains. So this is, in fact, the fact is the following. So by increasing the side chains, we shift the vibration frequency of the conjugated core toward higher frequencies. So it is known that actually phonons contribute to the dynamic disorder if they are thermally populated. So by this alteration in the frequency range, we decrease the number of phonons that are thermally that can be thermally populated, and as such, we are decreasing the dynamic disorder. The first one was also really interesting because if you look at the literature, the theoretical works that they assume a constant value for the relative dynamic disorder, they found that increasing the charge transfer integral does not increase the mobility. However, what we are seeing here is that increasing the transfer integral can decrease the relative dynamic disorder and implicitly can boost the mobility. And the final correlation was between the dynamic disorder and the presence of heavy atoms. In fact, we observed that the small molecules, the molecules that they have fewer atoms containing elements of heavier weight, they show larger values of dynamic disorder. So basically, in contrast to what we observed for the alkyl chains, involvement of heavy atoms in the molecular structures increases the number of low frequency phonons, and so they can easily be populated in the room temperature, and obviously they increase the dynamic disorder. Here, I've used these two simple molecules to explain this. if we substitute the hydrogen atoms in the left one by fluorine, so in the right one, we will have larger values of dynamic disorder. So basically, that brings me to the end. So what I have found in my research is that screening the Cambridge Structural Database enables making discoveries on materials. Now we have a collection of high mobility materials on structure property relationships. So now we have a list of parameters that they do affect the mobility, and we know the order of importance, and can lead to unanticipated design roles. So this like head-to-tail arrangement of the molecule is quite interesting. So just let me tell you, what I discussed in this presentation was related to the crystalline properties, but we have used the Cambridge Structural Database for single molecule properties as well. For example, we have identified a list of interesting non-fluorine acceptors, singlet fission molecules, and thermally activated delayed fluorescence molecules. So at the end, I just want to thank again the organizers and also in general the CCDC for providing this really disciplined database and all the useful tools we have provided, very helpful stuff. And thank you all for your attention. I'm happy to take your questions.
Thank you very much, Tahereh. That was a really interesting presentation, a great overview of some of the work that I know you've published. Please do put your questions for Tahereh into the chat box. I'm happy to kick off with the first question, though. I think previously I used to work in drug design and solid form design, and one of the ways that you would use to modulate properties there was to create a multi-component type system. So I was interested if in any of your searching you immediately discarded things that were more than a single component in the crystal, or if you did take on board things like co-crystals to look at modulating any of those kind of properties.
So basically, so far in my project, our focus has been on single component crystals, but in Liverpool, our collaborators are doing really interesting stuff on co-crystals, and probably we will extend the work to co-crystal as well.
Excellent. That sounds very interesting. I think there's probably some tweaking that could happen there with the crystal structures by looking at either polymorphs or additional components in there to the molecules.
Yeah.
Thank you very much again for a really nice presentation.
Thank you.